Welcome back to Probability and Statistics. This is our second of 10 lessons. We are in Chapter 3 in this lesson from Elementary Statistics, 4th edition by William Navidi. In this lesson, we are going to be looking at the three topics shown here: measures of center, measures of spread, and measures of position. If you think back to the last lesson, we looked at how to gather data. So we looked at how to do some random sampling. We looked at how to set up an experiment, things of that nature. And then we did dabble a little bit into how to display data through some various graphs and tables, things like that. In this lesson, we are now going to dive a little bit deeper into what do we do now that we have the data? How can we start to synthesize it, summarize it, begin to talk about the data in broader strokes rather than just sitting here with this whole mess of individual data points. So we are going to start with measure of spread, or excuse me, measure of center. Measure of center really gets into really two ideas: mean and median. A lot of times when you hear mean and median, you might also think of mode, mean, median, and mode. Mode, I am going to touch on in just a little bit, but mode is not actually a measure of center. And we'll talk about why when we get to that. But let's start with mean and just talk about what mean is. So mean is really just the arithmetic average. So when we think of mean, it's just that idea that we are going to take the sum of all the values, and then we are going to divide by the number of values. So sum of all values divided by the number of values. So for example, if we have the 6 test scores shown, if I want to find the mean of those test scores, the arithmetic average, I'm simply adding them together. And I'm going to divide by 6 since there are 6 of them. And so dividing by 6, that gives us an average of 80.5. And so when we hear things like what is the average test score, what is the average temperature, things like that, we're really talking about statistically the mean of that data. The other measure is median, and median is really more thought of as like the center or middle value of the data. And so in this case, one of the key things that we need to think about is if we're finding median by hand, we need to ensure that the data is in ascending order. Now, it could be in descending also, but typically we just think of it as ascending order. So lowest to highest. Because truly the way that we find median is we literally find the middle value of all of our data points. But again, there has to be order to that, or it's not going to make sense to find a middle value. So in this case, we're going to go through two examples because if you have an odd number or an even number of data points, it impacts how we actually find the median. So in the first case, we have 7 test scores. And so again, if we're just looking for the middle number, the first thing we need to do is make sure that those values are in order. And so we've got 56, 75, 78, 82, 87, 88, and 92. And so very simply, we are going to more or less count into the center. So if there are 7 of them, we want 3 on one side, 3 on the other, and our median sits right in the middle at 82. Now, in the second example, where we have an even number of test scores, again, if we put these in order first, we've got 56, 78, 82, 87, 88, 92. In this case, when I look to find the exact center value, there isn't one because it's sitting somewhere between 82 and 87. There's 3 values to the left of that position, 3 values to the right. So in this case, in order to find the median, we are going to take the average, the mean of those 2 values. We're simply going to add 82 and 87, divide by 2, and our median is 84.5. So that's how you find mean and median. Let's talk a little bit about kind of how they relate to each other and why we might use one versus the other. And so that gets us really into this idea of shape. And so when we talk about shape, we're talking about really if you were to think of like a histogram or a dot plot, what physically does that graph look like? Do you have a lot of values in the center and then maybe it tapers off to the left and right, kind of like a bell shape? Do you have a bunch of data that's really kind of to the left or to the right, and then just kind of scatters off to one side, things like that. And so the reason that shape is important is because it impacts whether or not we use mean or median. So let's think, for example, of how this works then, and how different values might impact a mean or a median. So let's take the idea of a seesaw. So if I have a seesaw and it's perfectly balanced, so that central point, that fulcrum, is right at the center of that seesaw will sit horizontally. It'll be balanced. If I put a weight on one side, that's obviously going to cause that seesaw to tip down, in this case to the left, hitting the ground. The right side is going to push up. But if I put a point exactly on the opposite side, exactly the same distance from the center, that seesaw will be back in balance. Thinking about that in terms of mean, for example, the average of those 2 points, if they have values assigned to them, maybe the fulcrum we think of as 0, and one value is 5, the other value is -5, the mean of those values is 0. In other words, that balancing point, when we think of mean, is truly the physical balancing point. So as I add another point, let's say on the right side, again, that's going to cause this to go down, but maybe I don't need to put a point exactly on the other side in the same place. Maybe I can put 2 points here. So as you think about numbers, I'm going to call this 4 and 5. I'm going to call this -5, and I'm going to call this -2. If you think about what the average is of those values, again, if we're putting this at 0, the average of those 5 values is 0. Okay, and so the mean is the actual balancing point of our values. And that's important because what happens is, if I put a point that's far away from all the others, not only does it cause that seesaw to go down, but it's going to take a lot more effort to get back to where we started at 0, so to speak. So let me give you an example of what I mean by that. Let's suppose that I have that I own a company, and I employ 49 people. So I have 49 employees. And just to be consistent, every single employee gets this paid the same. Every single employee gets paid $50,000. Okay. So the mean salary is $50,000. Everybody makes $50,000. Their mean is $50,000. All right. It also happens to be the median. If we were to look for the middle number, well, of course, they're all the same. So the median number, the middle number, is also 50,000. Okay. Now, there's me though. I'm the owner. I also draw a salary, and I'm kind of a greedy person. So I'm making 10 times what everybody else does. I make 500,000. So you can imagine now how that's going to impact the value of the mean and the value of the median. If we think of mean, if I want to find the mean, mathematically, I've got 49 employees, each making $50,000. So that's the sum of all of their salaries, plus the 500,000 that I'm making. And then if I divide that by 50, 49 employees plus myself, that gives an average salary of 59,000. So if I were to market my company and try to give people a reason to come work for me, I could say, for example, the average salary is $59,000. That's pretty good. Well, yes, that's true, but it's not really an accurate depiction of what's really going on in the company. Yes, the average salary is 59,000, but that's because my one salary is so high, it's taking the average of everybody else at 50 and bringing that entire average up $9,000. So mean would not be a very appropriate way to talk about center here, because it's not a very accurate measure of what's actually happening in our data. On the flip side, if you think about median now, median in this case, if I were to take all the values and line them up, I'm going to have a bunch of 50,000s, a 500,000 at the very end, but my median hasn't changed. My median is still 50,000. And so in this case, we would say that mean is non-resistant. In other words, it can't help but be pulled by large numbers on either side, extreme values. On the flip side, median is what we would say is resistant. When I add what would appear to be an outlier or something like that, the median is going to resist the temptation to be pulled by that. So, in other words, when we talk about shape now of our data, if I have symmetric data, let's try that again, symmetric. If I have symmetric data, that could look a number of different ways. It could be a bell curve, like I had mentioned earlier. It could look something like this. It could be something where you've got a lot of data on either side. So it could actually be something like this, where your data is on those ends and very, very little in the middle, so on and so forth. Okay. Point being, when it's symmetric, my mean and my median are both going to be at the center of that, at the physical center of that data. If it's truly symmetric, the average will be at the center. The median will also be at that same place. However, if I have data that is skewed, and there's two ways we can think of skew. We can think of skewed right. By the way, don't get confused by skewed right and skewed left. Skewed right, when we talk about shape, is really the direction that the data is being pulled. So in this case, to be skewed right means that my data is mostly on the left side, and then it's just being kind of pulled to the right. So I've got a lot of data all over here, and then I've got some data that just kind of trails off to the right. Likewise, if it's skewed left, then that data is sitting on the right side, and it's being pulled off to the left. So all my data is over here, and then it just kind of trails off to the left. So in this case, when we think about mean and median, my median might be somewhere like right here. That's the middle value of all those data points. If you think about what's happening to mean, just much like my salary of 500,000 pulled that mean far away from the 50,000, these values are going to pull that mean away from the median. So I'm going to exaggerate this, but my mean might be over here. Likewise, here's my median. And skewed left, my mean is going to get pulled somewhere towards those outlying values that are those skewed values off to the left in this case. All right. So in this case, then we would use mean typically when when your data is more symmetric. I'll give maybe a better way to think about this, a more clear way, because kind of the question is, well, what's considered symmetric and what's not? So another way to think of this is think of it as no strong skew or outliers. So if you're looking at your data and you're seeing a pretty strong skew, you probably don't want to use the mean. Or if you have an outlier, you wouldn't want to use the mean. In the employee example, my salary would have been an outlier. We wouldn't use the mean because that outlier pulls the mean away from the average or from the middle. Median then is going to be then used when you have any kind of skew or outliers. Now, again, there's always kind of a question, well, how skewed does it have to be? And I think you would just use common sense in terms of dealing with your data and what you think best represents the center. In some cases, you might offer up both values. You might give both the mean and the median as values if you're not quite sure how to handle that, just so that the person receiving that information can then make decisions about kind of what they think about the data from those values. Okay, let's move on here. So we've talked about how to find mean and median. The third one, again, that I had mentioned is mode. And again, mode is not a center of our data. It's not a way to talk about center. But again, because we often hear mode with mean and median, I thought it was important to kind of touch on. Mode just simply means most, right? So it's the value that occurs most often in our data set. So if you look at our two sets here in A, if you look at which one occurs most, 6 occurs most. So 6 is going to be our mode. In the second set in B, we actually have two values that occur 3 times. 6 occurs 3 times. And then 8 also occurs 3 times. So in this case, we would actually have 2 modes, 6 and 8. And when you've got 2 modes, we just say it's bimodal, meaning that there are two modes. All right. Okay, that's probably the last time in these lessons that we're going to talk about mode. But again, I just wanted to bring it up just to contrast it to the idea of mean and median. So what happens then if I want to find the mean and I don't have the exact values in the data set? So like in this case where I have a histogram, I have an idea of what the values are. I can kind of see shape here, and I can see kind of where the values tend to lie within certain ranges of values. But I don't actually know what the values themselves are. I can't add up the sum of all the values, divide by however many values there are, and get my mean. So in this case, the best we can do is simply approximate. And so the way that we're going to do that is we're going to take each bar and we're going to assume that the center of the bar roughly represents the mean of the values within it. So for example, in that first bar from 20 to 30, there are two values, right? We've got the frequency over here on the side, and the 2 tells me that there are two data points in that bar. Those values are somewhere between 20 and 30. They could both be very low, like 20 and 21. They could both be high, like 28 and 29. They might be on either side. We don't know, right? So I can only assume that if I took those two values and averaged them, took the mean, found the mean, that they would average to about 25, right in the middle of 20 and 30. So what I'm going to do is I'm going to say that both of those values are 25. So together, their sum is 50. And then I go to the next bar and I do the same thing. The average of 30 and 40 is 35. So I'm going to assume that the four data points are on average 35 each. If I take 4 times 35, then the sum of the points in that bar is 140. So I think you get the idea here. I'm not going to write all of these out, but as we keep going, if I were to do this for every bar, the next bar, for example, would have a total sum of 180, the next one 275, 195, 75, and 95. So this column represents the sum of all of the data points in all of those bars. And so if I add that all together, this is going to be basically the numerator in finding mean, right? This is my sum. I get 1,010. So to find the mean, I now just simply take 1,010. That's the sum of that's the estimated sum of all those values. And in this case, 2 plus 4 plus 4 plus 5 plus 3 plus 1 plus 1, right? How many data points are in each bar? If I add all those together, there are 20 values. So I'm going to divide by 20 and estimate the mean to be about 50.5. And if you think about where that is, 50.5 is kind of right on the right edge of that tallest bar. That seems to be a pretty good estimate for a central value of that data. Okay, let's move on then and talk about our next topic, which is spread. So when we talk about measures of spread, again, there are multiple ways that we can measure and talk about spread. We're going to talk about two of those in this lesson. One is range. I guess we'll actually talk about three. One is range, and range is probably the simplest, most straightforward. Very simply, it is the distance from the smallest value to the largest value in the set. And so if I have a set of test scores and I want to find the range, I'm simply looking for the largest and smallest test scores. And then I'm going to subtract those, 92 minus 56, and that gives us 36 for our range. Problem with range is that it doesn't give us a whole lot of information. So I know that okay, so for students in this class, based on this sample, the range is 36. So, okay, does that mean a lot of students did really well and there's one lower score? Were there a lot of low scores and one did really well? We just don't know. It doesn't really tell us a whole lot about the data itself if all we're given is the range. So another way, a better way to measure is what's called variance. And variance, by definition, is the average squared distance, or the average of the squared distances of the values to the mean. So the way that this works is, again, let's take 6 test scores. And if I want to find the variance, what I'm going to do is I'm going to take, I'm going to find the mean first of all. So the mean, in this case, adding those up would give us a total of 504. There are 6 of them, so dividing by 6 gives us a mean or an average of 84. Okay, so what's going to happen now is I'm going to find the average of the squared distances from those 6 values to the mean. So we're going to actually work that idea backwards. So I'm going to start with distance. So I want to find the distance from 70 to 84. Now, it doesn't really matter which order you subtract these in. I just typically do value minus mean, value minus mean, value minus mean. But it really doesn't matter, because once I find that distance, which distance should be positive, that value, I am going to square it because I want the square of that number. So ultimately it comes out positive anyway, which is why the order doesn't technically matter, unless you want to be critical and say that distance should be positive. So I should be doing 84 minus 70 to get a positive answer of 14. Point being, that is the squared distance from 70 to 84. If I do the same thing for 78, 78 minus 84 is negative 6. If I square that, I get 36. Now, I'm not going to do all the calculations here, but if I would do it for the next 4, I would get 1, 16, 25, and 100. So those are all of the squared distances from those values to the mean. Now I want to find the average of those squared distances. So I'm simply going to add them together. Adding them up gives me a total of 374. And to find the average or mean, we know that we divide that by the number of values. So to find the variance, we would take 374, and if you say divide by 6 because there's 6 data values, you'd be wrong. Okay, let's talk about this. I am assuming that these 6 test scores are from a sample of a larger group of test scores. Maybe 100, 200 students took the test, and these are just 6 tests from that group, or maybe just 25 students, doesn't matter. Because it's a sample, it changes how we find variance. And let me talk about why. Let's suppose that like a lot of times we think of test scores as kind of being kind of in that bell curve shape. So let me just assume that the test scores for the population, if we had access to all the test scores and we plotted those out, that it would kind of look like this. Okay, so imagine it being a histogram, whatever. All right. But it's going to have roughly that shape. So this curve represents all of the data for all of the tests in this population. Okay. If I take a sample of 6 test scores from this group, the likelihood that those test scores are going to come out of the extremes, in other words, the probability that I'm going to get the highest, or maybe even one of the top 3 highest scores, or one of the lowest 3 scores, is fairly unlikely from a probability standpoint. Most of the data is sitting right here. I would expect, again, just from a probability standpoint, that most of my 6 values that I sample are going to come from that more central area. So what happens is if I divide this variance, this 374 by 6 to get the variance, what this is doing, because it's based on a sample of 6, I'm really getting a variance that's based on that and not the entire graph. So to compensate for that and kind of correct for that, what we're going to do is we're going to divide by 6 minus 1. We're going to subtract 1 from our sample size. And when I divide by a smaller number, I get a bigger number. So dividing by 5 instead of 6 is going to give me a larger number, in this case 74.8. And that may not represent the entire variance. It might not get me from one end to the other, but it takes this and it spreads it out just enough to at least give us a better idea. Okay. So we're kind of stretching that out to account for the fact that we probably didn't get the extreme values when we took that sample. All right, so that is the variance. Now, again, variance not necessarily real helpful, but what we do with variance is we use our variance to get something that is more valuable, and that is standard deviation. Because standard deviation is nothing more than the square root of the variance. So standard deviation, I'll often abbreviate standard deviation SD, is simply the square root of the variance. So from our example above, the standard deviation is the square root of 74.8, which would be 8.65. All right, and what does 8.65 exactly mean? Well, again, we're talking about spread here. When we talk about spread, we're talking about exactly that. How spread out is our data? Is it clustered? Is it like all over the place? And what standard deviation tells us is typically how far would you expect the values to be from the mean? So, for example, in this case where we get a standard deviation of 8.65, if I was to interpret this in the context of the problem, what I would say is maybe something like this, that test scores uh, typically vary by 8.65 points from the mean test, or excuse me, from the mean, I guess mean score, test score of 84. So test scores typically vary by about 8.65 points from the mean score of 84. More specifically, what that means is if you were to add and subtract 8.65 from 84, you could say, yeah, typically you're going to expect scores to be roughly 77, 78, up to maybe 92, 93, right? That's kind of the range where we're typically going to see a lot of the values. That's what standard deviation does for us, okay? All right, so we've talked about mean and median. We've talked about standard deviation, variance, things like that. And so what I want to do is bring in some technology here, because if I go back to variance, the examples that I've been doing have had very, very small data sets, 4, 5, 6 values, very easy to work with, very easy to do by hand. However, typically we're using much larger data sets. So if I had a data set of, let's say, 100 test scores, I would not want to do this process 100 times, right? Each of those steps 100 times, add them all up, divide by 99, et cetera, et cetera. So technology is really our friend when we're doing a lot of this. And you can use any technology that you're comfortable with, that you're familiar with. I am going to use Excel. But if you wanted to use, for example, Google Sheets does the exact same thing as Excel. It's the same functions, it's the same keystrokes, everything. So Google Sheets, if you don't have access to Excel, certainly things like graphing calculators, certain finance calculators, statistical calculators can obviously do this. There's obviously statistical software programs out there as well. So whatever works for you, whatever you have access to. Like I said, I'm going to use Excel because you can do pretty much everything in these lessons that we're going to do in Excel. And that's what's going to be my kind of go-to for technology. So how do we do that? Well, I've kind of got this already set up for us. I've got our 6 test scores already typed in, and you can do it in a column. You can put them in a row. You could, even if you wanted to, you could do something like this where you just have 2 rows of 3. It doesn't really matter. Because what you're going to do is whenever you want to find a value, whenever you want, like in this case, Excel to calculate something for you, you just start typing in equals. So for example, let me do this off to the side. Let's say I wanted to just simply add up all those values. I could say equals A1 plus A2, giving positions. A1 is the cell, A2 is the cell. I'll just do those two. If I want to add those two together, right, it's going to give me 148. So you can do a lot of just very simple calculations, a lot of arithmetic with Excel. But there's also a lot of functions built in. So if I want to find the mean, I don't have to type in, this plus this plus this plus this divided by, this. I can just say, okay, I want the average. Excel uses the word average, not mean. So I'm going to start just typing in after I hit equals. You want an equals to say I'm about to find a calculation. I'm going to type in AVE, and what I get is average, which is what Excel uses. Now, at this point, you can type out the word, or you can just hit Tab, and it will finish everything for you. So we're finding the average, And now it's asking, what do you want to find the average of? What values? Well, I want to find the average of the values in column A. So you could, if you just notice when I click on or when I highlight A, I've got a little down arrow there. If I just left click here, it will select the entire column. A to A just means everything in column A. And if I do that, I will get the average of all the values in column A, 84. Or if I wanted to, I could be a little more specific and I could say, well, no, I really just want the average of these 6 values. So A1 colon A6 means the values from A1 through A6. And if I do a parenthesis to close it out, I get that same average of 84. What's the difference? For this purpose, none. But let's say I wanted to add a 7th test score. Let's say I add a 67. It's not going to change my mean. In fact, it tells me with this little green corner, there's a problem because now your formula doesn't match up your data. Where if I did average of A to A, I'm just going to type it in, A to A, right? Now it gave me a new mean because I added in 67. If I take 67 out, I'm back to 84. So kind of want to think about that as you think about, if you are using this for school or work or some setting like that where maybe you are going to be changing data, working with larger data sets, you want to have that flexibility in how you set this up. Okay, median. Median is exactly that. If I just start typing in median, there's only one option. What do I want the median of? I'm just going to use the 6 values for this purpose, 86.5. Variance, again, if I just start typing in variance equals variance. In this case, I get a number of options that kind of have this VAR in it. What we're looking for is VAR.S and P. So these first two that appear in my options. .P always refers to population. .S always refers to sample. So in this case, I want .S because I'm assuming that these 6 test scores are a sample from a larger population. So I'm going to choose this. Again, what do we want the variance of? These values. All right, standard deviation. Well, again, depending on the information you have, there's different ways to find standard deviation. Remember, for example, that standard deviation is the square root of variance. So in Excel and Google Sheets, SQRT is square root. I can take the square root of that cell D4, and that's going to give me that 8.65. Or more practically, I could just find the standard deviation because oftentimes if you're finding standard deviation, you're probably not finding variance anyway. So I'm going to do equals ST, and already I start to see here's that .P, that .S, stdev.p, stdev.s. So standard deviation for the population, standard deviation for the sample, that's the one I want. For these 6 values, I get the same standard deviation, 8.65. Okay, so that's how you can use Excel to do these. And again, as I work through the remaining 8 lessons in this series, I will continue to come back to Excel and show how to use Excel to do those various calculations. All right, so coming back to our notes then, let's talk about, or let's do an example similar to what we did before. So this is that example where we have a histogram, so we don't have the exact data values, but we want to estimate or approximate, in this case now, the standard deviation. We did this for the mean before. So again, we're going to use a very, very similar process, but just with standard deviation. So kind of cutting to the chase here, we know if already from the previous example that the mean of this data set is 50.5. So now what I want to do is I want to find the standard deviation for each of those points. Basically what I'm going to do is go through the variance steps that I did up here. But when I get these values in this last column, instead of just accepting those values as they are, I'm going to multiply them by however many data points are in each of those bars. So for example, for the first bar, I'm going to take 35. I want to keep consistent here. 35 minus 50.5, right? That's the difference. And then square that. That's the squared distance. But in this case, because there are 2 data points in that bar, I'm going to multiply that by 2 because this technically represents the value for each of those. When I do that, that gives me 1,300.5. I'll show it one more time. For the next one, we're going to use 35. Whoops, I'm sorry. That should be a 2. The value is correct. The answer is correct. I just wrote 35 instead of 25. The next one is 35 minus 50.5 squared. This bar has 4 values, so we'll multiply that by 4, and that is 961. All right, now again, I'm not going to show show this for all of the bars, but if I were to keep going, the next bar would have a sum of 121, 101.25, 630.75, 600.25, and 1980.25. So again, those are all of those squared distances, but representing all 20 data values, not just 6 bars, right? It's counting the individual values within each of those bars. So if I add that all together, I get 5,695 on the dot. So to find variance, again, I'm taking that value, not divided by 20, but divided by 20 minus 1, because again, we'll assume that that's a sample. And so divided by 19 would give us a variance of 299.74. So our standard deviation, taking the square root of the variance, is going to be 17.3. Well, where did that come from? Let's put it down here. 17.31. All right. Okay, so that's how we can do that same type of example for standard deviation. So let's kind of wrap up this section by talking about some notation for mean and standard deviation. Then I want to just kind of get a little bit more into that bell-shaped curve that that I referred to earlier. So when we talk about notations or symbols, there are different symbols depending on whether or not you are talking about population or sample. And so this is where you have to really pay attention to the symbols being used. When we talk about the mean for a population, we are using the symbol mu, the Greek letter mu, for population. If I'm talking about the standard deviation for the population, I'm using the Greek letter sigma. Okay? So mu for mean, sigma for standard deviation, both for population. If I'm talking about the sample, for mean, I'm going to use an X with a bar over it. And this is literally read X bar. If I'm talking about standard deviation for the sample, it's just an S. Sometimes you'll see a subscript X there. So that's just S sub X or just S, depending on how that's written. But you really want to make sure that you know these and have these clear, because a lot of times you might just be told mu equals 17. What is mu? Is mu mean, standard deviation? Is it population? Is it sample? So very much, these are important symbols to know in statistics because they're used quite frequently. All right, the last thing before we get into the final section on position is to come back to that bell-shaped curve that I was talking about earlier. So in statistics, in an elementary statistics class like this bell-shaped curve is a very, very important thing to us. And we're going to see this and use this quite often. This actually represents very specifically what we're going to call a normal curve. Okay, this is a normal curve, or we just say that our data is normal. What that means very specifically is, again, remember this curve is representative of all the values from a data set for the population. Okay, so you've got a lot of data in the center area, tapers off to the left, tapers off to the right. So we know that if this is symmetric, that the mean is going to be in the center. There's that mu. I'm going to put some tick marks here, and those tick marks are going to represent one standard deviation away from the mean. So this would be one standard deviation away from the mean, 2 standard deviations, 3 standard deviations, and then going the other direction, we can do the same thing, -1. Negative, positive to denote if you're above or below the mean. Okay, so you can be a positive one standard deviation below the mean. We can say it like that. But if we were to just write it out as -1, it tells the reader you're below the mean, not above the mean. -2 standard deviations, -3 standard deviations. Okay, so what the whole point of this is let's take our let's just say I have an example, and the way we would, by the way, the way we'd label this is n for normal. We'd specify what the mean is, and we'd specify what the standard deviation is. And I'm just going to make up some numbers here for purpose of this example. So if our mean is 75, that means that the value here is 75. If the standard deviation is 5, that means that this is 80, 85, and 90. This is 70, 65, and 60. Okay. Why is all this important? What's the point of all of this? Well, the point is that if you have a normal data set, if you've got a curve like this, we know that generally speaking, about 68% of your data is going to lie between -1 and 1 standard deviation. In other words, 68% of your data is going to be within 1 standard deviation on either side of that mean. So in this case, we could say that we would expect about 68% of our data to be between 70 and 80. 2 standard deviations out is 95%. And 3 standard deviations out is 99.7. So you have a very, very, very small percentage of data that is typically more than 3 standard deviations away from the mean in a normal curve like this. Why this is helpful is very simply, let's say I want to start, we're going to start talking about position here in a minute, but I could say, for example, then that I would expect 95% of my data. Let's say these were test scores, right? So again, the average test score is a 75. Standard deviation is 5, which means typically scores vary by about 5 from the mean, right? Well, what we're really saying is this. We're saying, yeah, about 2/3 of the data is within 5 of the mean, from 70 to 80 in terms of a test score. 95% of our data is going to be between 65 and 85. Almost 100% between 60 and 90. So very, very few we would expect to get above a 90. Very, very few we expect to get below a 60. All right. As we start to talk about position, it's also helpful to recognize then that if I have a score of, let's say, a 77, let's say my score is right here at 77. Well, that's a decent spot to be. I'm kind of on average. I'm above the mean. That's good. I'm better than 50%. And I'm kind of in that middle section. So I'm kind of in that 2/3 of students who are getting a score of 70 to 80. If I have a score of 89, right, I'm out here, I'm way out here. Well, that's really good, right? I'm outside of that 95%, which means if I'm outside 95%, from here to the right is 2.5%. On the other end, from here to the left, is also 2.5%. So if I have a score of, let's say, anything above 85, I'm in the top 2.5% of scores. Flip side is if my score is below a 65, I'm in the bottom 2.5%. So that's not good. And if I get a score above a 90, well, then I'm in really small company, because above a 90, this is 0.015%. And same on the other side. So I'm in a very, very elite group of students who are getting above a 90 on this test. Okay. So we can kind of use this as a baseline or kind of a generalization, not only to get a sense of where is our data, what is the spread, okay, but also now as we transition into position, this is also helpful in terms of that. Measures of position then is exactly that. It's where is a particular data value in relationship to all the other values. And so we kind of just talked about that a little bit. But we're going to talk specifically in terms of 2 ideas. One is this idea of z-score, and then the other is going to be percentile. So z-score is another fairly big idea in elementary statistics. When we talk about a z-score, we're talking about exactly what it says here. It says tells how many standard deviations a value is from the mean. So it talks about position in terms of standard deviations. The way that we find z is to take the value minus the mean of the population divided by the standard deviation. So in words, I'll write this out, is the sample value, so the value that we have that we're using, the population mean, and then the standard deviation. In this case, it's very important that we actually do that numerator in that order. You always want to take the value minus the mean, because when we do that, positive and negative will tell us whether or not we're above the mean or below the mean. All right, let's take a look at a couple examples here. So a reading test has a mean score of 75 and a standard deviation of 10 when given to third graders. Ava scored a 71. How many standard deviations above or below the mean was her score? So again, very simply, Z is her score, 71, minus the mean of 75 divided by the standard deviation of 10, which gives us a value of negative 0.4. So what that means then is that Ava's score is basically zero point 0.4 standard deviations below the mean. That negative again means that we're below the mean. Positive would mean that we are above the mean. Okay. Similarly, it says the same test has a mean score of 82 and a standard deviation of 11 points when given to sixth graders. Asa scored a 75. How many standard deviations above or below the mean was his score? So again, similarly, we're going to take Ava's score of 75 minus the mean of 82 and divide that by the standard deviation of 11. And in this case, his number of standard deviations is a negative 0.64, which again means then that his score is 0.64 standard deviation below the mean. One of the things that z-score is very useful for is in a situation like this where we're kind of comparing apples to oranges, but we still have a similarity that we want to look at and try to see who actually performed better. So if we look at Ava's score, for example, the third grader, she scored a 71. Asa, the sixth grader, scored a 75. So by score alone, Asa did better. However, the z-score tells us where they rank, basically, or where they're positioned in relationship to their peers. So Ava, though she had the lower score, actually kind of did relatively better against her other third grade peers than Asa did against his sixth grade peers. She was only 0.4 of a standard deviation below. He was 0.64 of a standard deviation below. So comparatively, we would say Ava actually did better because for third graders, she outperformed compared to how Asa did to his sixth grade cohort. So that's kind of one of the usefulnesses, or usefulnesses. That's one way that z-score is useful in looking at data and talking about the position, comparing data, things like that. We're going to see in a future lesson how z-score then is also used to find area under the curve. In other words, how much data is to the left or to the right of that value. Okay, so let's talk about the other one then, which is percentiles. And percentiles, probably a term that many are familiar with. It's the data at or below a percent. This is what's often used when we take standardized tests like the ACT or the SAT. You'll get your raw score of 31 on the ACT or a 1280 on the SAT. But you also often get a percentile, right? You're at the 80th percentile, you're at the 64th percentile. And that percentile tells us how you did compared to your peers. So in this case, we're going to say a percentile, which we'll just call P, separates the lowest P% of data from the highest, and technically 100 minus p percent of data. So it's maybe a little bit of a goofy notation, but if you think about it, if I'm at the 80th percentile, then that separates the lowest 80% from the highest 100 minus 80 or 20%. In other words, if I'm at the 80th percentile, 80% of scores are below mine, 20% of scores are above mine. All right. So let's go ahead and just do an example with this. And we're going to kind of look at this in both directions. Oh, by the way, I should probably give you a formula here first. Let's talk about how we find percentile. So to find percentile, we are going to take the number of values that are less than x, and we are going to add 0.5 to that. And I'll explain why in just a minute. And then we're dividing that by the number of values in the set. Now, when you do this, you're going to get a decimal, and we want a percentile. A percentile is always an actual percent, 77, 69, 48, whatever. So we need to multiply this by 100, okay, to put it into that whole number. Which, speaking of a couple of things here, and then I'll talk about the 0.5 in relation to this. First of all, we need to be sure that the data is ordered. So again, much like finding median, we want to make sure that our data is in order from lowest to highest. And then secondly, we want to always round to the nearest whole number. So after you've multiplied by 100, put this into a 76.8 or whatever, we always round to the nearest whole number. And the reason for that is because percentiles are always whole numbers. You're at the 87th percentile, you're at the 47th percentile. You are never at the 92.5 percentile, right? You're never at a decimal percentile. That is part of why we add that 0.5, because what that does is it basically, especially where you have whole numbers for data, it's going to put you in between values. So when you're calculating this out, then and you're rounding the nearest whole number, it should then kind of adjust and put you at the correct percentile for that. So if we take a look at an example, it says, given the following weights in pounds of babies at birth, find the 70th percentile, and then at what percentile is 7.5 pounds. I'm actually going to do these in reverse order. We're going to start with B and then come back to A, because B is just a direct use of this formula. And then we're going to come back and do A, and I'm going to give you a different formula that basically just kind of reverses the process. So we're going to take the number of values less than X, not less than the value, add 0.5, divide by the number of values in the set, multiply by 100. So again, we're on B. At what percentile is 7.5 pounds? So here's 7.5 pounds. So that's our X. So we want to know how many values are below 7.5. And in this case, there are 4 of them. So to find the percentile, we take 4 plus 0.5 divided by the total number of values in the set. So we count those up. We have 2, 4, 6, 8, 10, 12, 14 values. Again, that gives us a decimal. So you could get the decimal and then just know to convert it to a percent or multiply by 100. But that's going to give us basically the 32nd percentile. Okay. So if you have a baby who at birth is 7.5 pounds, at least according to this data, they would be at the 32nd percentile. Okay, so the part A then says, now kind of reverse it. What value is at the 70th percentile? So we found the percentile in B. Now you have the percentile. We want to know the value that represents the 70th percentile. So to kind of turn this equation around, and I won't go through the kind of the math of that, but basically what we're going to do is we are going to basically use this formula. L is the position of the value. That's what we're finding, because once we know the position, we can count out then and find the actual value. P is percentile, and then N is the value. Or excuse me, the number of values in the set. Okay. So in this case, if I want to find the location where the number is, I'm going to take the percentile 70 divided by 100 and then times 14. What I get is 9.8. Okay. Now, we're talking about positions here, right? It's in position 1, 2, 3, 4. So 9.8 doesn't make any sense. We are going to round this to 10 and call this the 10th value. I should note that you always round up when you do this. So if we had gotten an answer of 9.1, we would not round down to 9. We would round all the way up to 10. Okay, so you always round up no matter what that decimal is, no matter how small. So in this case, we count the 10th value. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 10th value is right here at 8.2. So 8.2 is at the 70th percentile. And I abbreviate percentile with a little percent sign and then ILE. Okay, so that's how you find the value, kind of just working that formula backward that we used in B. Okay, well, let's move on here, and we are going to kind of extend on this idea. So let's talk about quartiles. So quartiles are basically fourths of data. So quartile 1, for example, would be the first 25% of your data, often abbreviated Q1. So this is basically the 25th percentile. 25% of your data is below, 75% is above. Quartile 2 or Q2 is going to be the 50th percentile, half below, half above. Where have we seen that before? That is right, with the median. Q3 is the 75th percentile. So 75% below, 25% above. Okay. Q4 is the 100th percentile, which means everything is below. So that really doesn't make sense to talk about Q4. So we really just talk about Q1, Q2, Q3. But if you think about kind of a line of values, if I use those three values, here's Q1, Q2, and Q3, it cuts it into 25%, 25%, 25%, and 25% of data. Okay, so that's what we mean by quartiles or fourths of data. All right, so one of the ways that we use this then is when we want to create what's called a box plot. You may know what a box plot is already, but in order to create a box plot, we need what's called a 5-number summary. And that 5-number summary is made up of a minimum value. So what is the smallest value in your data set? Q1, so that 25th percentile. I'm going to use the word median here, but again, that would just be Q2 as well. Q3, which is the 75th percentile, and the maximum or biggest value in your data set. So what this does, if you don't know what a box plot is or have forgotten, box plot is the thing that kind of looks like this. And basically what you've got is this is the min, this is Q1, this is the median, Q3, and the maximum. Okay. Let me clean this up a little bit for you. There we go. Okay. And each part of that box plot represents 25% of the data. So this tail, or this sometimes called whisker, is 25%. This is 25% of your data, 25% of your data, and 25% of your data. All right. So again, a box plot is basically kind of just representing visually those quartiles. All right, so the other thing we need to talk about then in relation to this, and then we'll actually create a box plot, is this idea of outliers. Now, I should mention when we're constructing a box plot, if I have an outlier, what I'm going to do is I'm going to represent the outlier by an asterisk. And you can have more than one outlier, so you might have multiple asterisks. The max then really isn't the maximum. That outlier is the maximum value. The max that ends this bar, this little tail, is going to be the next lowest value in the list. Okay, well, we'll see that in the example that we do. And the reason that we do that is because you may have an outlier that's far away from all the other data. It's part of the data, so you don't want to necessarily ignore it. But if I were to draw this bar all the way up to this outlier, it makes it look like there's 25% of data in that range, in that distance of that bar. When in reality, it stops here, and then there just happens to be one value far away. So it gives us a better idea of where the data is actually fitting or sitting, rather than kind of extending that all the way out to that outlier. Okay, so how do we find an outlier then? So we're going to use what's called the interquartile range. When I was talking about spread earlier, I said that there were three ways we could talk about spread. I only talked about two of them. I talked about range. Remember, range is the total distance from the lowest to the highest value in your data set. And then we talked about kind of that idea of variance and standard deviation. Interquartile range is the other way that we can talk about spread. What interquartile range is it's the distance from Q3 to Q1. It's basically the length of the box in the box plot. It's the middle 50%. So it's, again, because you might have outliers and things like that, that if you were to use range, might cause a really large number that isn't truly representative of the data. So when we do interquartile range, we're guaranteed that that is the middle 50% of the data. And so whatever that range is, we can say if the range is 20, oh yeah, so the middle 50% is 25 to 45 or whatever it happens to be. And then outside of that, obviously, it could go up to 150 and down to negative 4,000. But we know then that those are clearly extreme values. And this is what the middle 50% is doing. A lot of times we will use interquartile range to describe the spread when your data is skewed or you have outliers. So remember, we talked about mean when it's symmetric, median when it's skewed or outliers. Same thing here. Interquartile range when it's skewed or you have outliers, and then the standard deviation when it's symmetric. Okay. All right, so that's interquartile range. It's the range of the middle 50% of the data. And we use this to find basically boundaries to determine where our outliers may lie. So the lower boundary is found by taking Q1 minus 1.5 times the IQR. And then the upper boundary is found by taking Q3 plus Q3, not 8.3, Q3 plus 1.5 times the IQR. What we're essentially doing is saying, take that box, blow it up 1.5 times, and basically attach it to the end. So we're kind of just saying, okay, we're going to give kind of say that we're in this box, we're allowing this size plus another 50% of itself to go this far and this far. Anything outside of that, we're going to call an outlier. Okay, so it's just kind of setting up a boundaries for that. So let's do an example. We're going to go through a full example here of creating a box plot. I guess I'll do this. So just kind of have a clean picture here of what a box plot looks like and all the values. Again, things may be look very weird and different. Could look like that. I'll put a couple outliers on this end. So again, this would be an outlier. I'm going to call this the min, but again, it's technically not the min if there's an outlier. It would be the next lowest number. Q1, your median. Q3, again, the maximum, biggest point unless you have outliers. And then it's just the next lowest. It's basically the biggest point before you hit an outlier. On the other end, it's the lowest point before you hit an outlier. Okay, so let's go ahead and do an example here. So make a box plot for the following data set. So it's already in order, so we don't have to worry about that. Because again, we're finding median. Well, we know how to do that. And I'll show you how to do Q1 and Q3. It's basically the same process as finding a median. So median is the middle value. So there are 2, 4, 6, 8, 9 values. So we are looking for the fifth one in, so that there's 4 on either side. So that's our median. Okay. Because this is an odd number of data values in the set, and 11 therefore is our median, when we find Q1 and Q3, we're really finding the middle of the upper half and the middle of the lower half. In this case, when we look at the upper half, we are looking at just values bigger than 11, and when we look at the lower half, values less than 11. So we're going to ignore 11 in finding Q1 and Q3. So on the lower end, we're looking for basically the median of 7, 8, 10, and 10. Well, that falls between 8 and 10, so Q1 is the average of 9, just straight up 9. And then on the other side, it's the average of 14 and 18, which is 16. That's Q3. Now, I'm going to say max here because that's our biggest value, and I'm going to say min here because that's our smallest value. But again, how we actually plot this may change depending on outliers. So let's go ahead and check for outliers. And again, to do this, we're going to find a lower boundary, which is taking the Q1, which is 9, minus 1.5 times the IQR. The IQR, again, is Q3 minus Q1. So 9 minus 1.5 times 7 is going to give us a value of negative 1.5. And then the upper boundary is Q3 16 plus 1.5 times 16 minus 9. And that is going to give us 26.5. So anything outside of those values are going to be considered outliers. Well, clearly on the lower end, 7 is our smallest value. That's bigger than negative 1.5. So there are no lower outliers. But the upper outlier boundary is 26.5. 28 is bigger than that. And so 28 is an upper outlier. Okay. So when we graph this, 28 is no longer the max that ends that tail. It's actually going to be 18 that will end that tail. So let's go ahead and graph this. When we graph, we do want to give a scale. So I'm going to just 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Clearly should have done a little bit smaller there, but that's okay. 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, and 28. All right. Now you can do this however you want. I tend to like to make the box first and actually start with kind of the end. So Q1 and Q3. So Q1 is 9. Q3 is 16. So here's 9. Here's 16. And so connecting those two gives us the box of our box plot. And then our median is 11. So at 11, we're just going to draw a line right down through the box. Now on the low end, on the left side, again, 7 is our minimum. So at 7, we're going to have the end of our tail. And then on the high end, because 28 is an outlier, we're going to put an asterisk there. And then again, as I mentioned earlier, we'll stop at 18. So at 18, we're going to stop that upper tail. So that's what our box plot looks like. Okay, well, that's actually it for this lesson. That was a lot. Mean, median, again, make sure you know how to find those. The idea that mean is used when you have symmetry in your data, or basically no strong skew or outliers. Median when you do have that skew or outliers. We talked about spread, range, variance, and standard deviation. Again, standard deviation typically when you, again, don't have strong skew or outliers. I'm going to jump right down to this idea of IQR for the other idea with spread that we'll typically use if you do have skew or outliers. And then just this idea of making a box plot. So the z-score we will definitely use quite a bit more in future lessons. So you're going to see that one quite often. Otherwise, that's it for this lesson. I hope that it's been helpful to you, and I look forward to seeing you in the next lesson.